Welcome to the video lecture on Unit 2 Dynamics. The section is on the gravitational field. First of all, we want to talk about the difference between mass versus weight. Here you are given a 10 kilogram object. This is considered to be the mass. The mass is 10 kilograms. We can put this mass on a scale, and that scale can exist on Earth. The mass is now on a scale. The question asks, what does the scale read? The scale would actually read 100 newtons or 22.5 pounds. It does not read 10 kilograms. It reads 100 newtons or 22.5 pounds. The scale is actually showing the force of gravity that the 10 kilogram object experiences. Note, your weight is the same thing as the force of gravity on you. So the 100 Newton is actually the force of gravity that the object feels that is shown on the scale. The scale measures the force of gravity. It measures your weight. A scale does not measure mass. It measures the force of gravity that object experiences. Likewise, if we were to take the same mass, which is that 10 kilograms, onto the moon where the gravity is 1.6 of Earth, we can say that what is the mass on the moon? It would be still 10 kilograms. The mass is still the same. The mass does not change. It's still 10 kilograms. What does the scale read? What is the weight? It would read 60 newtons or 3.6 pounds. Why? Because the gravity on the moon is less than that is on Earth. That's why the scale would read it less. Again, because the scale measures the force of gravity. Note, your weight is less on the moon because the gravitational field of the moon is less than that is on Earth. You want to complete this table below on two objects. For the first object, you know it is 60 kilograms. And the second object, you know that it is a 120 Newton object. So, first question, what is the mass of the 60 kilogram object? It's still 60 kilograms. Nothing changed. But what is the mass of the 100 Newton object? Well, you would have to do the force equals mass times acceleration and solve for mass. The force is 120 and gravity is 10. You do that division, you get 12 kilograms. So the mass is 12 kilograms. What is the weight of the 20 kilogram object? What is the weight of the 60 kilogram object? Well, it would be 60 times 10 because this is the gravity. So it would be 600 newtons. What about the 100 Newton object? Well, it's still 100 newtons because this is the force of gravity. What about the mass? Well, mass is still going to be the same. It's still 60, so this is still going to be 60. Mass does not change when you move the location. Nothing is lost. Likewise, this is still also going to be 12 kilograms because again, mass does not change when you move to a different planet. What does change is actually gravity. The weight on the moon, where gravity is 1/6 of Earth. So here we use 1/6 because this is the factor of the moon of Earth. And this is Earth's G right here. So you do 1/6 of 10 times 60. So it is 100 newtons. Notice right here, the weight or the force of gravity is less because the moon the moon has a smaller gravitational field. Likewise, if you do the same calculation, 1/6 of the 120, it should get you 20 newtons because this object is going to have less weight. It has a less force of gravity on the moon as well. It is 1/6 less. So we saw how it changes or affects the mass. We saw how gravity affects the mass. So we need to look at the force of gravity as the weight, which is a force. Weight is the force of gravity on a mass or an object. We write it as just F equals to ma. That is the force equation. The acceleration just becomes g. This is the force equation for the force of gravity. Acceleration becomes gravity. In short, we call that the gravitational field. The acceleration is the g, which is the gravitational field that accelerates the mass. Here's some information about the gravitational field, or you could call it gravity field. 1. All masses are surrounded by a gravitational field. This is the advanced image of what a gravitational field is. It's the warping of space-time. Notice the big mass of the Earth is bending this fabric around it. That is essentially like the gravitational field. Notice the gravitational field is a long-range force that will accelerate the smaller object towards it. So the bending of this mass will force objects to accelerate towards it. Notice objects have a different value for their own gravitational field. It depends on its mass, shape, and size. Notice the Earth is big, that's why it bends it down this much with its gravitational field. Look at the moon, which is smaller. It only bends it down a little bit, so it has a smaller gravitational field. The moon has a small gravitational field because it is smaller than Earth. That is why it falls within our orbit. Experiencing the force of gravity. When you sit or stand, the force of gravity does not disappear. It is actually balanced out by the normal force. So here you are. You would see that the force of gravity goes down. Then you are, due to Newton's third law, there's a normal force that goes up. N minus Fg equals to 0. This is when you are in balance. This is when you are in equilibrium. The way I think about this is I weigh 200 pounds standing or sitting. It does not change unless I lose fat. Now, why do you fall down? You will only fall down if the normal force disappears. So notice N disappears, so it just becomes Fg. So that will be equal to mass equals to mass times acceleration or gravity. So you fall down because gravity is actually pulling you down always, but you're falling because there is no more normal force. That normal force disappears. That balances it out. Because there is no more normal force, you fall down. Remember, gravity doesn't change during the situation. Now let's look at the relationship between the mass force of gravity and the gravitational field. Okay, mass is m, force of gravity is Fg, and gravitational field can be looked at just g. So if I ask for you to solve the gravitational field, I'm just asking you to solve for g. So what you can do is just divide m to both sides. Once you divide m to both sides, you get g is equal to the force of gravity divided by mass. You now want to fill in the relationship between all these different values. Now, if the force of gravity increases while mass stays constant, what happens to the gravitational field? So we can just write the proportion. G equals to Fg over m. The force of gravity increases, so this goes up. Mass stays constant, so we can just ignore this. What happens to the gravitational field? Well, that has a direct relationship. It is on top of the fraction, therefore gravity has to go up. So we can say that the gravitational field increases as a result. Next, let's write it again. As mass increases while the weight of the object stays constant, what happens to the gravitational field? So we're looking at G is equal to Fg over m. Now here they say mass increases. So mass increases and the weight of the object, which is Fg, stays constant. So we can just ignore that and we can just write it as a 1. What happens to the gravitational field now? Well, the m is on the bottom, so that means it has an inverse relationship. So if n goes up, g goes down, all right? Because you're dividing by a larger number. So we can say that the gravitational field decreases. How can the force of gravity increase while the gravitational field stays constant? So how can the force of gravity, which is Fg, increase while the gravitational field stays constant. So this stays the same. So this becomes like 1 because it stays the same. If this goes up, mass has to go up as well. Yeah. Because if this goes up by 2, for it to stay the same, this also has to go up by 2. So do you see 2 over 2 just becomes 1? So if one goes up, the other one has to go up for it to remain balanced. So for gravity, so for the gravitational field to stay constant, if the force of gravity increases, the mass also had to increase as well. If the mass remained constant, but is now on a different planet where the gravitational field is weaker, like on the moon, what happens to the force of gravity that I will experience? So let's take a look. G is equal to Fg over m. Mass remains constant, so the m just becomes a 1. But now the gravitational field is weaker, so Fg goes down. What will be the gravitational... the gravitational field I feel. I'm sorry. So the gravitational field goes down, so the G goes down. What happens to the force of gravity? Well, if this goes down, this also has to go down because it has a direct relationship. So I will feel a weaker force of gravity. So Fg goes down. All right? Next, here are some conceptual questions. Here, an object of mass 10 kilograms is released from rest above the surface of an unknown planet. The graph displays the object's velocity as a function of time. The force due to gravity exerting on this object is most nearly what? Again, this question is asking you for f of g. So here's the solution. You set up the equation. Force of gravity equals to mass times acceleration, but you don't know what the acceleration is on this planet. So you have to use the change equation. So the acceleration is just the change of v over the change of t. You can tell by that graphically. I grabbed these 2 points, which was 2, 8 and 1, 4. And I did the slope equation. I saw that it equals to 4 meters per second squared. That is the acceleration. Now I plug it in. The mass is 10. Right here, mass is 10. And I saw here that the acceleration is 4 meters per second squared. Plug it in. Multiply 10 times 4 is 40 newtons. So I would say that the force due to gravity on this planet is 40 newtons. So this is like Earth. No, this isn't like Earth because the acceleration is 4, which is like almost half of ours. Next, 2 identical 10 kilogram objects are dropped from a height of 100 meters above the surface of 2 different planets, planet Q and planet P. The graph here displays the velocity as a function of time as the object undergoes free fall. Which planet exerts the greater force of gravity on the sphere, and what evidence supports the conclusion? Well, I would say planet Q because the slope here is greater. The slope here is greater. The fact that the slope here is greater, m is greater, therefore the a is going to be greater. So the greater the velocity slope means the greater the acceleration, because again, the acceleration is the change of v over the change of t. So acceleration can be seen as the slope of the velocity versus time graph. There you go. So that is everything that you need to know when it comes to the gravitational field.